Welcome to the Mathematics 23 review slides by the UP Mathematics Club. Here we'll be discussing a bit more on triple integrals. Last time we discussed triple integrals as mass. So if you want to find the mass of an object, you take the triple integral over some solid g of rho dv, where rho is our density function. And dv, since we were doing it in rectangular coordinates, is dx, dy, dz. Here, we will be focusing mainly on getting volume instead, which is actually a lot more simple, because while it is the same triple integral over the solid g, it just has dv. So this is how you get volume. You just set rho equal to 1, and you'll get the volume of a surface, of a solid. So just as a reminder, we're doing dv is equal to dx, dy, dz. The order is of course determined by how you integrate, but the general concept is that we're using Cartesian coordinates. Of course, you can do triple integrals in other coordinate systems, but we'll discuss those later. So if that's all, let's get into the problems. So compute for the volume of the solid bounded by the surface z is equal to the square root of y, and the planes x plus y equals 1, x equals 0, and z equals 0. So I'm going to give you guys some time to pause and think about how to solve this problem, or maybe even solve it for yourselves. So let's get into the solution. Last time, in order to solve these kinds of problems, we first drew the surface, then we found the bounds, and then we integrated. So in these problems, we're going to be focusing more on finding the solid, visualizing it, and setting the bounds. Because the integration will be somewhat straightforward because it's just dv as opposed to rho dv, but the surfaces will be a bit more difficult. So let me try to draw this. So we have z is equal to the square root of y, but this is just z squared equals y, where z is greater than 0. So if we have this thing, then it's just this half parabola shape. That's z is equal to square root of y. But that's just in 2D. In 3D, this becomes a cylinder extended along the x-axis. So let me just draw this x. Let me just draw the 3D axis. Where this is z, this is y, and this is x. So it's a half parabola. Wait, let me use another color. So it's a half parabola. And then in order to extend the cylinder, we just draw the parabola, the half parabola somewhere else and then connect them. So what about the planes? X equals 0 and z equals 0 are actually easy. Let me just note that this is the brown surface. The maroon surface, OUP, is this over here. That's x equals 0. And the sky blue surface is the thing on the bottom, z equals 0. In order to draw the plane x plus y equals 1, we can think of it as a cylinder where its sort of like projection is just a line. So if we look at x plus y equals 1, we know for sure that 2 points on x plus y equals 1 are 1, 0 and 0, 1. Are 1, 0 and 0, 1. I got it backwards. So it's this. So we can draw this. We can draw this and then extend it. And that's our plane. So it might be a little difficult, but I was just going through the graph here to show you guys how you could graph it. Thankfully, we have an actual figure. So as you can see here, this red surface is our half parabolic cylinder. Z is equal to the square root of y. And then this dark blue plane is our x plus y equals 1. And then these two light blue planes, they're the coordinate planes, x equals 0 and z equals 0. So what is our solid now? Well, it's the place that all of these planes or surfaces surround. This is our solid G, this thing I've outlined here in black. So you'll notice that we say that this solid G is of type YZ. Looking at it, I think it can actually be of type XY or type XZ integration. We just chose YZ for these purposes because you do have to choose one to integrate it, but we should still get the same answers. But where it will differ is the amount of work that you have to do to get that answer. So for type YZ means that our dV is equal to dx dA. And then our dA is determined by how we integrate the YZ projection, which I will show in the next slide. So this is our YZ projection. So for this tutorial, we decided to do vertical rectangles. You can still do horizontal. It should still be okay. It should still give you the same answer. But we chose to do vertical. So we're going to be doing dz, oh wait, no, dx, dz, dy. That's going to be our order of integration. So all that's left now is to find the bounds. And we'll start with dx. So for reference, this is the x-axis. So the bounds of this are this light blue plane over here, this light blue plane over here, and then this dark blue plane. So the light blue plane is just x equals 0. So we can say that the lower bound of x is 0. While the upper bound is x plus y equals 1. But we just have to write that in terms of x. So if we transpose the y to the other side, we get x is equal to 1 minus y. So those are our x bounds. Now, if we look at the YZ projection for the next bounds, we have to do z first, and z is this blue axis. So the upper bound for z is the half parabolic cylinder, square root of y, and the lower bound is 0. And for y, it's actually a lot simpler, because as you can see, the figure is actually labeled. Y goes from 0 to 1. So the question is, how can you determine that this is 1 if you don't have a labeled figure, for example? Well, you just have to look at this, at your original 3D figure, and the intersection and the end of the y, this point over here that I'm mousing over, let me just mark it. This point over here is at the intersection of this light blue plane, this dark blue plane. But remember that the dark blue plane is x plus y equals 1, and the light blue plane is x equals 0. If we combine both of these, we get the condition that y equals 1 at this black point. So that's how we know that the upper bound is 1 without having, tick marks on our graph. So now we've gotten our boundaries. So it should be relatively easy from here on out. We are past the hard part. Here we go. Thus, this is our triple integral. Now I'll be going through this very quickly. So here, in order to integrate by dx, you just have to write an x and then evaluate it at 1 minus y and 0. So that will just leave you with 1 minus y. And you do the same thing with d, and then remember that another one of the bounds is 0, so you get square root of y times 1 minus y. So far this has been pretty okay. Then we just multiply these two quantities together. So we get square root of y minus y square root of y, or in other words, y to the 1/2 minus y to the 3/2. We write it in this form so that we can do the integration a lot easier because of the power rule. So by the power rule, this becomes this, and thankfully another one of our bounds is 0, so we only have to evaluate it at y equals 1. So this just becomes 1 over 3/2 minus 1 over 5/2. So it's just 2 over 3 minus 2 over 5, and that's 4 over 15. So let's move on to problem 2. In problem 2, we just have to set up the triple integrals for this solid. but we have to do it in type XY, type YZ, and type XZ. Okay, before I start discussing the problem, I'll let you guys think about the solution first. Okay, so let's figure out what to do here. So again, I guess the best way to start is by drawing the surface. So let's draw it in green. So it's in the first octant, which means that the coordinate planes are some of our bounds. And then our final bound is this plane passing through the points 1, 0, 0, 0, 2, 0, and 0, 0, 3. So let's mark these points. Wait, let me just show that these are X, Y, and Z. A, and then here is B, and then up here is C. So we just have to have the plane that passes through all those points. So this is our tetrahedron. Now we have to determine the bounds. And to do that, we need to know what this plane is. Like, what's the equation of this plane? So we first have to find the equation of the plane. Now, if you don't remember how to do this, we have to start by taking two vectors on the plane. Okay, let me bring back the drawing. We have to take two vectors on the plane. We'll take their cross product, which in theory and in practice actually will give us the normal vector. This is a normal vector. And then using the normal vector in one of these points, A, B, and C, we can find the equation of the plane. But first, we need two vectors. An example of a vector could be this vector here from A to C, or this vector from B to C, or this vector from A to B. For this problem, we only need two of these vectors, and it doesn't matter which one we'll choose, we'll get the same direction for our normal vector. And direction is the only thing that's important. So we chose A, B, and AC here. So how do you get these vectors? Well, you just have to figure out what do you have to add to A to make it go to B, for example. B is 0 to 0, and then A is 1, 0, 0. So in order to get from A to B, you have to subtract 1, add 2, and then just leave the z coordinate untouched. That's why it's negative 1, 2, 0. So that's A, B, and AC, our two vectors. So we just need to take the cross product. I'll show you the formula for the cross product here, just in case you forgot. And I'll leave you to verify that it is indeed 6, 3, and 2. Okay, I'll clear this drawing so you can see it, 6, 3, and 2. Okay, so now we have the normal vector, which remember we needed this. We needed normal vector. So we just need to take one of these points. For our solution, we chose point A. A is 1, 0, 0. So it becomes x minus 1, y minus 0, and z minus 0. So that's for the quantities here, the things inside the parenthesis. So we just need to multiply these parenthesized quantities by 6, by 3, and by 2. And there we have the equation of the plane, which we can simplify as this. So now that we have the equation of the plane, we can get to solving, or rather setting up. For sub-item A, we need to do a type XY. So let me just refresh you guys that if you have a type XY solid and you want to integrate it using a triple integral, you write it like this. You write it as a single integral dz and then a double integral dA, where dA is either dy dx or dx dy. It depends on which projection you choose. We need to figure out what the bounds are. So let's take a look at our diagram again. The most important benefit of being in only the first octant is that the coordinate planes are our lower boundaries. So in other words, this is x equals 0, this is z equals 0, and this is y equals 0. Those are all the lower boundaries. So this u1 here, it's automatically 0. What about u2? u2 of xy is just this plane, but we need to write it as z. So what we do is we take the plane equation from the previous slide, and then we solve for z. So you transpose x and y, and then you divide by 2. So that's the upper boundary. How about for our dA? How do we do that? Well, we just need to get the projection. So in order to get our projection, so I'll give you a visual for how we can get the projection. So when we say get the projection, we mean get this area over here. We want to get the projection onto the xy plane, and that's this sky blue area. So how do we get it? Well, we just take the equation of the plane, and then we set z equals 0. And then we should get this, line over here. And if we draw that line, it should bound the area that we need, the projection. For example, we need to get the projection onto the YZ plane. Well, that would look like this. And then we'd have to set x to 0. So if we go back, we just have to set z equal to 0 here. For example, we can just cross that out. And then this, whatever is left, that's our equation. 6x plus 3y equals 6. That's our equation. Okay, we're not going to show how we got the bounds for the double integral, the xy projection, because we assume that you guys can do it. But just remember that there are two ways to do it, vertical rectangles and horizontal rectangles. And we chose to do it with vertical rectangles, which is why our y has a variable upper bound. So after we get the boundaries for the xy region, we just have to write it all down like this. So remember, the upper bound is the plane, and in the lower bound you have the projection of the plane, and then here you have constant boundaries, which are determined by a, b, and c. So the iterated triple integral is this. Okay, so let's move on to type yz. Okay, so for type yz, we have dx as our first variable. But let me bring up the drawing again. If you look at x, if you look at it from the x perspective, the lower bound is this red thing over here. It's still 0. And the upper bound is still the plane. So similar to z, we just have to find the equation of the plane. We have to transform the equation of the plane into an equation that's x equals something. And that will be our upper bound. So that's our dx. So for dA, again, you guys can either choose dy dz or dz dy. What's important is that you get the projection of the plane when x equals 0. So you get 3y plus 2z equals 6 when x equals 0. For us, we did z first, then y. So again, these are the bounds, and this is the iterated triple integral. Okay, so finally, I guess we have sort of a formula here already. We know that this u1 is just 0. This is just 0. And at this one, you just need to take the plane and then rewrite it as y equals something. And then for dA, again, you just have to project, but this time, set y equal to 0 for the equation of the plane. That's your projection onto the xz plane. And then perform the double integral over that region. So we get the projection of the tetrahedron, so on and so forth. So the projection of our plane onto that xz plane is 3x plus z equals 3. So again, choose whether you want to do z first or x first. We decide to do z first. And just write it as an iterated triple integral. Now we skipped over a lot here. We skipped over the evaluation, how you can get dA, because that's just a double integral and it's not really the focus. The real focus of this is how to get the triple integral. So we need to focus on the third bound.